Hey humans, and welcome back to my science studio. In today's lesson, we'll be starting a brand new series on the mole concept. Today we'll be talking about what exactly a mole is, what Avogadro's number really means, how to convert between moles and particles, and how to calculate the molar mass. So without further ado, let's just get to it. Okay, what is a mole? You see, one thing I love to ask my students is this. If I tell you to buy me a dozen roses, how many roses would you buy? 12, right? What about a dozen eggs? 12. A dozen golden doodles? Still 12. You see, it doesn't matter what the item is, whether that's roses, eggs, cute dogs. The answer will always be 12 because a dozen equals 12. And so the mole works the same way. According to Amedeo Avogadro, 1 mole of anything equals 6.022 times 10 to the 23rd. That number is called Avogadro's number, and it is a constant, meaning it doesn't change. So 1 mole of anything equals 6.022 times 10 to the 23rd of anything. But what is anything? It can be atoms, molecules, formula units, ions, anything. And just as a little disclaimer, I do round to 3 sig figs, and most teachers and professors do the same. So it is okay, as long as your teacher allows it, to report Avogadro's number as 6.02 times 10 to the 23rd. But anyways, okay, but why do we even use the mole to begin with? You're probably wondering. Well, the mole allows us to measure very large quantities of very small particles. You see, atoms and molecules and ions are microscopic. We can't count them individually, so we can group them together, just like we group eggs into dozens. Let's take a couple examples of how we use the mole. You see, 1 mole of a monatomic element, for example, carbon, right? So 1 mole of carbon is equal to 6.02 times 10 to the 23rd carbon atoms. 1 mole of a diatomic element like fluorine gas, right, is equal to 6.02 times 10 to the 23rd fluorine molecules. 1 mole of water, right, H2O, is equal to 6.02 times 10 to the 23rd water molecules. And just a little quick clarification before I keep going. The word molecule is typically used for covalent compounds, so between 2 nonmetals. For ionic compounds, like for example NaCl or sodium chloride, we use the term formula unit instead. Remember, an ionic bond is between a metal and a nonmetal. So 1 mole of NaCl is equal to 6.02 times 10 to the 23rd formula units of NaCl. And formula unit is abbreviated capital F, capital U. So you get the gist, right? It's the same number, just a different type of particle. Now let's go ahead and try a problem step by step where we will be converting between particles and moles. The question reads, how many moles are in 2.42 times 10 to the 24 atoms of gold? The first thing you want to do is write what you're being given. And because we're being asked how many, let's put a question mark here. How many moles, the mole is abbreviated MOL, of AU, gold, are in, that's your equal sign, and the question is giving you 2.42 times 10 to the 24 atoms of gold. So we set up our problem with what we're being asked equals what we're being given. Now we're going to open a parentheses and draw a fraction. We want to go from atoms to moles. Remember, atoms, it's a type of particle, right? So we can use Avogadro's number to help you go from the atom to the mole. How so though? Well, ask yourself, what can I put in the denominator as far as units are concerned to cancel out my atoms of gold? Right, Avogadro's number. So if we put the 1 mole of AU at the top and the 6.02 times 10 to the 23rd atoms of AU at the bottom, we are able to cancel out the atoms of AU and be left with moles. So plugging this into our calculator, you take 2.42 times 10 to 24 and divide that by Avogadro's number. And your calculator should give you something like 4.019933, something like that, right? But chemistry is all about being precise, right? So we have to use significant figures here. If you look at the question stem, we have 3 significant figures. So our answer should be reported to 3 significant figures. So if we look at this 1 and look next door to it, it's above a 5, right? 9 is above a 5, so we can round up. So to 3 significant figures, we get 4.02 moles of AU. Now I encourage you to pause the video and try the next 2 problems on your own first. And when you're ready, press play and we'll go through them together. So the first question reads, how many moles are contained in 3.2 times 10 to the 22 molecules of H2O? So you first start off with what you're being asked. So you write a question mark, how many moles of H2O are in what you're being given? 3.2 times 10 to the 22 molecules of H2O. Now, similar to the last example, we have molecules, the type of particle, right? And we want to get to the mole. So we can use Avogadro's number. So if we open up a parentheses and draw a fraction, we can say that in 1 mole of H2O, there are 6.02 times 10 to the 23 molecules of H2O. Why do we write the molecules on the bottom? So that we can cancel them out and we're left with moles at the top. Now, when you plug into your calculator and you divide 3.2 times 10 to 22 divided by Avogadro's number, you should get something like 0.05315614, etc. Remember, one way that we can express really big or really small numbers like this one is in scientific notation. And oftentimes your teacher or your professor will want it in scientific notation. And also remember that it has to be with the correct number of significant figures. And in the value 3.2, we should round the answer to 2 sig figs. So keeping that in mind, look at this decimal and move it 2 places to the right because we want to reach a number between 1 and 10. So our answer should read 5.3 times 10 to the negative 2. Because we moved the decimal 2 spaces to the right, it's 10 to the negative 2 power moles of H2O. And remember, it's 2 significant figures. That's why we cut it off at the 3. Because when we look next door, it's a 1. And because it's less than 5, you drop it. And that's our answer. Now in the next problem, you're going to see that we're going to be going in the other direction. So the question reads, how many formula units are present in 0.80 moles of silver chloride, or AgCl? So again, start off with what you're being asked. Question mark, so how many formula units of AgCl are in what you're being given, 0.80 moles of silver chloride? Notice that in the last example, we started with particles, right? Molecules or atoms in the other example that we did, and we wanted moles. But here we have moles and we want to get to particles. In this case, we want formula units. Remember, formula units are reserved for ionic compounds, so between a metal and a nonmetal. So if we're starting with a mole and we want to get to formula units, we're still going to use Avogadro's number. But when we set up our fraction here, you put the 1 mole of AgCl at the bottom. Why? Because we want to cancel out our moles. And at the top, we place Avogadro's number. So just bear that in mind that depending on what you're being given in the problem, that's going to dictate the units that you place either in the numerator or in the denominator. Now, going ahead and plugging this into our calculator, you can see that now we're not dividing, we're actually multiplying. So we take 0.80 and we multiply that by Avogadro's number. And my calculator actually already gives it to me in scientific notation, so yours may as well. And I end up getting 4.816 times 10 to the 23rd. But remember, you have to report with the least number of significant figures, okay? So in the question stem, it gives me 0.80. We have two significant figures here. Remember, zeros to the left of a decimal don't count, they're insignificant. But that zero after the 8 does count. So definitely brush up on your significant figures rules when you get the chance. So reporting to two sig figs, you look at the 8, look next door. 1 is below a 5, so you drop it. So the answer is 4.8 times 10 to the 23rd formula units. Now, before we wrap up today's lesson, let's talk about molar mass. Molar mass is the mass of exactly 1 mole of a substance, and the units will always be grams per mole, often indicated as G/mole. And I can't emphasize this enough that it's always per 1 mole. The mole carries the 1. But anyways, if you look at the periodic table, the decimal number underneath each element is its average atomic mass. And that number also represents the element's molar mass. So in the example of carbon, in 1 mole of carbon, there's 12.01 grams of carbon. Now, what if you want to find the molar mass of a compound? Well, we can just take the sum of the atomic masses of all the atoms in that chemical formula. So for example, let's say you want to find the molar mass of CO2, carbon dioxide. First, identify the number of atoms of each element present. Well, in CO2, we have 1 carbon and 2 oxygens. Then you go to the table and you find the atomic mass of each element. On the periodic table, carbon is 12.011. My periodic table, there's a little bit of extra digits, so definitely be comfortable using the periodic table that your teacher gives you. But anyways, so if we multiply 1 times 12.011, we end up getting the molar mass of carbon in CO2 to be 12.011 grams per mole. And oxygen is 15.999 times the 2 present here, we end up getting 31.998 grams per mole. Now, adding these two numbers together, we end up getting 44.009. And let's say your teacher asks to round to 4 significant figures. Well, we count, and we see that we end at this last 0 here. So look next door to it. It's above a 5, so we're going to round up. So your answer should be 44.01 grams per mole of CO2. And before we move on, there's a quick disclaimer I'd like to say about rounding. You'll notice that when I calculate the molar mass, I don't really round as I go. I carry all the decimals through my calculation and only round at the very end when I have to report the correct number of significant figures. And so some periodic tables, maybe the ones your teacher provides on your test, they may have atomic masses that are already rounded, and that's completely fine. The most important thing is that you stay consistent with whatever periodic table your teacher gives you. I personally prefer not to round along the way because it keeps the final answer as precise as possible, and that's what chemistry is all about, right? Being precise. But again, always follow your teacher's instructions and use the periodic table provided to you. But anyways, okay, once again, I encourage you to go ahead and pause the video and try these 2 problems on your own. And when you're ready, go ahead and press play and we'll walk through them together. The first question reads, find the molar mass of chlorine gas, rounding to 4 significant figures. So this is a trick. Remember your 7 diatomic elements. Have no fear of ice-cold beverages. Chlorine gas likes to exist as a diatomic. So you have to write Cl2, where the subscript 2 tells you that there's 2 chlorines naturally bound together. So you have to multiply the atomic mass of chlorine by 2. So we take 35.453 grams per mole of chlorine times 2 chlorine atoms, and we get 70.906. Rounded to 4 significant figures, we get 70.91 grams per mole of Cl2. Now in the next problem, we want to find the molar mass of calcium nitrate. So we're going to have to break this down carefully. So counting the number of atoms here, we have 1 calcium, 2 nitrogens, and 6 oxygens, because remember, 2 times 3 gives us 6. Now the molar mass of calcium is 40.078 times 1, that's just 40.078 grams per mole. Nitrogen has a molar mass of 14.007 times 2 atoms of nitrogen, we get 28.014 grams per mole of nitrogen. And lastly, for oxygen, we have 15.999 as the molar mass for oxygen times 6 oxygen atoms, and we get 95.994 grams per mole. The last step is to take the sum of these 3 values. So we end up getting 164.086. Rounded to 4 sig figs, we get 164.1 grams per mole of calcium nitrate. Okay, you guys, so today we learned a lot. We learned about what the mole is, what Avogadro's number represents, how to convert between moles and particles, and how to calculate molar mass. In our next series of videos, we'll be combining these concepts, right? We'll be using molar mass and Avogadro's number into more complex conversions, and eventually to one of my favorite lessons, stoichiometry. If you found this lesson helpful at all, please don't hesitate to like and subscribe to my channel. And as always, if you'd like extra practice problems, please leave a comment below. I am always happy to create more examples. I'll see you next time in my science studio, but until then, happy studying.